Hello everyone. In today's discussion, we'll be talking about junction capacitances in a semiconductor diode. And for the basic understanding of diode, it is clear that in the depletion region of a PN junction diode, we have negative immobile ions towards the P-type semiconductor material and positive immobile ions towards the N-type semiconductor material. This is the P side and this is the N side of the semiconductor material. This region is nothing but the depletion region of the diode. This is the depletion region. Depletion region. Now, this depletion region works in a semiconductor diode as a parallel plate capacitor, because one plate is being considered as a negative, equipped with the negative ions, and another plate is may be considered as a positive charge, positive ions, positive immobile ions. And the capacitance C in this case for a semiconductor diode is given by, that is simply A epsilon naught into epsilon r divided by the width of the depletion region, that is the W. This Cj that I'm writing, that is equivalent to your Cj is junction capacitance in a semiconductor diode, is simply A epsilon naught epsilon r divided by W, and it has a unit of farad. So Cj can be Cj, we can say that this junction capacitance is inversely proportional to the depletion width of a semiconductor diode. It is inversely proportional to the width. It means that if the width of the depletion region in a diode will increase, this junction capacitance is going to decrease. And with the equation of W, it is also clear that this W is inversely proportional to the doping concentration, square root of doping. So we can equate these two equation 1 and equation 2, and it can be concluded that the junction capacitance in a semiconductor diode is directly proportional to the doping concentration. It means that if the doping of the P side or N side is going to increase, the junction capacitance is going to increase. And if the depletion width of the semiconductor diode is going to increase, this Cj is going to decrease. And there is one more relation here, this related to doping and the depletion width, and this width is inversely proportional to doping, means if the doping is going to increase, the depletion width is going to reduce, and if the depletion width is reducing, the junction capacitance is increasing. So this is basically a junction capacitance being created in a semiconductor diode. Now when we are going to bias our semiconductor diode in forward bias or in the reverse bias, this capacitance dominates in a different way. And in this way we classify, we have two types of junction capacitances here. The first one I'm writing here as transition capacitance, that is your transition capacitance, and it is nothing but your Ct. And the second one is the diffusion capacitance, diffusion capacitance, this is your Cd. This transition capacitance is mainly comes when your diode is being operated in the reverse bias condition, and this Cd is going to dominate when your diode is going to be operated in the forward bias region. Now first of all we'll be talking about this transition capacitance Ct. Now Ct is the transition capacitance, and we also call it as a space charge capacitance. There is another name for this Ct is space charge capacitance, and it dominates when your diode is being operated in reverse bias condition. Ct, it somewhere you can write it as C mu. All right, Ct is given by A epsilon divided by W. So again we can conclude here that Ct is directly proportional to A, and this transition capacitance is inversely proportional to this width of the depletion region. And what happens when your diode is being operated in the reverse bias condition? For reverse bias, we can say that the depletion width W is going to increase, hence CT is going to reduce. And one more thing, this CT is inversely proportional to the applied voltage. Here I am writing it as N. N is nothing but your constant, and it depends on which type of junction is being used in a semiconductor diode. There are different types of junctions such as step graded diode. This N is constant and this CT is inversely proportional to the applied voltage, and the value of N depends on which type of junction are we having, such as we have a step graded junction, step graded, or abrupt junction diode, abrupt junction diode. Now in this case, this N value is being taken as is given by 1/2, and for there is another junction that is your linearly graded. In this case, N value is given by 1/3, and there is a diffused PN junction diode. This is also one type of junction, diffused junction. Right, in this case this N value is nothing but your 1/2.5. So these are the various values of N for different type of junctions, semiconductor junction diode. So here we can conclude that this CT, transition capacitance, dominates when a diode is going to be operated into the reverse bias condition, reverse bias region, and it is inversely proportional to the applied voltage. It is inversely proportional to the applied voltage. For example, if we are considering it as step graded diode, for this N is taken as 1/2, and we can say that CT is going to be inversely proportional to the what? Applied voltage. In this case, this VBI, this is nothing but your built-in potential plus whatever be the reverse bias voltage is applied across the diode. CT is inversely proportional to this VBI plus VRB. This is your transition capacitance, and it dominates when your diode is going to be operated in reverse bias condition. And this property of transition capacitance is being utilized in the designing of this varactor diode. This is one of the diode, varactor diode, in which CT, its working totally depends on the transition capacitance, and this diode is being operated in the reverse bias condition. Generally, the CT value should be as small as possible. If we compare the CT value of the diode, semiconductor diode, or with the with the BJT, bipolar junction transistor, the CT value for BJT is smaller than the CT value of the semiconductor diode. That's why BJT gives better performance whenever it is being compared with the diode with respect to this transition capacitance. So this is all about the transition capacitance in case of a reverse biased PN junction diode. Now we will be talking about this diffusion capacitance, and it is also called as, second one is a diffusion capacitance. Diffusion capacitance, that is CD. We also call it as storage capacitance. Storage capacitance, CD. Now the CD is because of the change when a diode is going to be operated in the forward bias. Now when the diode is forward bias, what is happening? There are the charge carriers from the P side, they are holes, and they are going to be transported towards the N side, and in the N side they are becoming the excess minority carrier in the in the N-type semiconductor material. All right. So due to the change in the excess minority carriers in the P side or N side, when the diode is being operated in the reverse bias, in the forward bias, this diffusion capacitance is going to dominate. The diffusion capacitance CD is, again we can write it as in general form A epsilon divided by W. And what do we have when the diode is going to be operated in the forward bias? The depletion width, this in the forward bias is smaller than the depletion width of the diode in the reverse bias. So we can say that this CD value is going to be always greater than this CT value in a semiconductor diode. CD, diffusion capacitance or the storage capacitance, is always greater than this transition capacitance in case of a semiconductor diode. Alright, for the better performance, for the better working of the semiconductor diode, this CD value should also be as small as possible. Now there's one more equation for CD we can write. It is CD is given by tau times of G. This tau is nothing but the mean lifetime. It is the mean lifetime of minority charge carriers. And G is nothing but your conductance. It is conductance, and G is also, it is equals to 1 by resistance. So CD we can write as diffusion capacitance CD is nothing but simply tau divided by the resistance, the diode resistance, and this diode resistance R is given by eta Vt divided by IF, forward current of diode, eta Vt divided by IF, because in this case the diode is being operated in the forward bias, and in the forward bias this CD is going to dominate. So we can write here CD it as CD, this diffusion capacitance is equals to tau times of IF divided by eta Vt, tau times of IF divided by eta Vt. So by seeing this equation we can conclude few of the points that comes in various examination, in which region this diffusion capacitance is going to dominate in case of semiconductor diode. So when the diode is forward biased, the CD will be dominating. The second question, for example, how this CD depends on the forward voltage across the diode. So how can we say this CD is directly proportional to IF, and this IF is exponentially depends on the forward voltage across the diode. So we can say that this CD increases exponentially with respect to the forward voltage that we are applying across the diode. So CD is exponentially dependent on the forward voltage that we have applied across the diode. Alright, so these are the few of the points that you have to take care of while studying this transition capacitance and the diffusion capacitance. Okay, all right, thank you so much. At this point we will stop here, and if you have any doubt or any query, you can drop me a mail, or you can also comment on the video section, comment on the comment section. All right, thank you so much. Thank you all. For any query you can write down my email id, d.shekhar91@gmail.com. So for any query you can mail me on this email id. All right, thank you so much.